Section 13.3, partial derivatives. So in this section, we're going to take derivatives of multivariable functions with respect to a single variable. So we're going to treat all other variables as if they are constant. So let me give you an idea of what I mean here. Suppose I have f of x is equal to 3x. Then f prime is equal to 3, right? We all know that. Excuse me. If I have got g of x equal to pi of x, not pi of x, goodness sakes, pi times x. Take the derivative, pi is a constant, just like the 3 is a constant. We get g prime of x is equal to pi, right? Now suppose I give you h of xy, and that's equal to y times x. And I say, well, we're going to take the partial derivative with respect to x. Well, if x is the only variable I'm interested in being variable, the y might as well be constant, and we're going to treat it that way. So the partial derivative of h with respect to x of xy is equal to y, because we're treating y as though it were a constant, just like 3 or pi, right? All right, so let's mix it up a little bit. Let's change it up just a touch. Suppose I had 3x squared, then f prime of x would be 6x. If g of x were pi x squared, then g prime of x would be 2 pi x. If h of xy were equal to yx squared, then the partial derivative of h with respect to x of xy would be 2yx. So these derivatives are going to happen exactly in the same way as we've always taken derivatives. The only difference is we are treating our other variables as if they were constant. So here's one more for you. Suppose I have f of xy is equal to y. And I said, well, what is the partial derivative of f here with respect to x? Well, relative to x, y is a constant. So the derivative of a constant is 0. That means that there is no change in the x direction of this function. Okay? So that's the general gist of what we're going to be doing with these partial derivatives. Okay, so let's now define the partial derivative. All right, given f of xy is equal, let's say z is equal to f of xy. Let's do that. Then the first partial derivative, because we have first derivative, second derivatives, etc., same thing. So the first partial derivative of z with respect to, so WRT with respect to x, is denoted f sub x of xy, or the partial with respect to x of f of xy, or z sub x, all right, is given by this formula. So we have the limit as delta x approaches 0 of f of x plus delta x, comma y, minus f of xy divided by delta x. Okay, so this is just like the derivatives that we had seen in the past. This one's with respect to x, so it's f of x plus delta x minus f of x. It's that corollary there, right? Okay, and the same thing is going to be for the derivative with respect to y. We'll have the first partial derivative with respect to y denoted f sub y of xy, or the partial with respect to y of f of xy, or z sub y, will be given by, or is given by, the limit as delta y goes to 0 of f of x comma y plus delta y minus f of xy all over delta y. Okay, so this is our partial derivative with respect to y. And this will be our partial derivative up here with respect to x. And of course, this assumes that that limit exists. Now, this notation, the partial, when I was very clearly saying partial, that's actually what we call that notation. It looks to me like a backward 6. So we have, oh, that was terrible. We have the partial of f with respect to x. We have the partial of f with respect to y. We can have the partial of f with respect to z, etc. Okay? And just like with regular derivatives, if we want to take second derivatives or so forth, we could say the partial squared of f with respect to x squared, right? We can set it up like that, that sort of thing. So we'll talk more about that in just a moment. First, let's go ahead and jump in and do some examples using partial derivatives. So example, let's take f of xy equal to ln of x squared plus y squared, and let's find f sub x and f sub y. So we're looking for the partial derivative of f with respect to x, and then the partial derivative of f with respect to y. So f sub x. Now, because I'm taking this partial with respect to x, I'm going to treat y like it's just a regular, everyday constant. I'm not going to treat it like a variable, nothing special. I'm just going to treat it like it was a 2 squared sitting there, or a pi squared sitting there, right? Okay, so the derivative of ln is 1 over the argument, which is x squared plus y squared, chain on the derivative of the argument. Well, the derivative of x squared with respect to x is 2x. And the derivative of y squared with respect to x is 0, because that's constant with respect to x. So this comes out to be 2x over x squared plus y squared. Okay. Similarly, fy, we have a y inside the argument, so this is going to be 1 over x squared plus y squared, chain on the derivative with respect to y. So now x is constant, so the derivative is 0, and y squared has a derivative of 2y, so this comes out to be 2y over x squared plus y squared. So let's do another example. Same thing, let's find the partial with respect to x and the partial with respect to y of f of x, y, equal to x times e to the x squared y. All right. So, first things first, partial with respect to x of f of xy. Now, if I look at this in terms of x being my only variable, I see that I'm going to need product rule because I've got an x times e to the x squared y. So we need to treat this thing using product rule. Okay, so again, the y is constant with respect to x. I treat it like it's a pi or a 2 or any constant. Okay, so the derivative of x is 1 times the second e squared y plus the first times the derivative of the second. So e to any power gets repeated. Then we chain on the derivative of that power. So x squared y, y is constant. I don't care about that. So the derivative of yx squared is 2yx. So we chain on 2yx. Okay, so this comes out to be e to the x squared y plus, okay, so we've got 2 times a y times an x. So that's 2 times x squared times y, e to the x squared y. And there we have it. There's our derivative, with our partial derivative with respect to x. So now let's find the partial with respect to y. So the partial with respect to y of f of xy is equal to, okay? Now I'm going to go back up here and erase these green parentheses that I had drawn because we don't need product rule now. X is constant with respect to y, so it's like a 3 or a pi or something like that sitting there, just constant. So I'm only concerned about where the y's are, and y only occurs here in the exponent of e. So this is going to be x times the derivative of ex squared y with respect to y. So that's ex squared y, chain on, and the derivative of x squared y with respect to y would just be x squared, because x squared is a constant, y is linear. So we're just chaining on the constant, in air quotes, the constant from the linear term. So then what we end up with here is x cubed times e to the x squared y. And there's our partial derivative with respect to y. Okay, so what are these doing for us? These partial derivatives with respect to x or y are describing the change in the direction of x or in the direction of y. So we are looking at this and thinking, well, how much is this going to change in the x direction? From this point, what's the rate of change in the x direction? Or from this point, what's the rate of change in the y direction? So it's very analogous to slope, this whole idea of the partial derivative. Very, very analogous to slope in 2 dimensions. All right, so let's do an example where we're actually asked to find the slope in those directions. So let's find the slope in the x and y directions at the point 1, 1 for f of xy equal to 1 minus x minus 1 squared minus y minus 2 squared. Okay, so we are going to find the partial derivative with respect to x, and then plug in the values for x and y, and then we're going to plug in the, then we're going to find the partial derivative with respect to y and do the same thing. So let's find the partial derivative with respect to x. 1 is constant, so the derivative of 1 is 0, minus x minus 1 quantity squared. So we multiply the 2, subtract 1, and then chain on the derivative of x minus 1, which is just 1. Okay, and then the third term, minus y minus 2 quantity squared. There's no x in that term. That term is constant with respect to x. So therefore, that's the derivative is 0. And this is what we're left with, negative 2x plus 2, if I distribute the negative 2. Okay. All right, so at the point 1, 1, the slope is minus 2x plus 2. Oh, I can't say the slope is. I have to say the slope in the x direction is, because there's 2 directions we're working with, right? So the slope in the x direction would be negative 2 times, plug in a 1 for the x, plus 2. So that's negative 2 plus 2 is equal to 0. So we are not going to see any change in the x direction from this point. Now let's do the partial derivative with respect to y. So that's going to be, let's see, partial derivative of 1 with respect to y. That's 0 because 1 is constant. X minus 1 quantity squared. Well, there's no y there, so that's constant. So that's also has a derivative of 0. And then minus y minus 2 quantity squared. So that's minus 2 times y minus 2 to the 1. Chain on the derivative of y minus 2, which is just 1. Okay. So this just comes out to be negative 2 plus 4. Negative 2y. Drop the y. Negative 2y plus 4. And then we put in our point. So at the point 1, 1, the slope in the y direction is negative 2 times 1 plus 4, which is positive 2. So in the y direction, the slope is 2. And so if we continue to increase, that's the rate of change we would see at that instant. Okay, so now let's take a look at functions with more than 2 variables. So it's going to work in exactly the same way. We are going to let w of x, y, z be equal to xy plus yz squared plus xz. And we're going to find all 3 first partial derivatives. We're going to find all 3 first partial derivatives. Okay, so that would be wx, wy, and wz. So wx, we are going to hold y and z constant. So if the term does not have x in it, that term goes to 0. That's the derivative of a constant term is 0. So I've got 2 terms containing an x, an xy, and an xz. So the derivative of xy is y. The derivative of xz is z. So we have y plus z. There's the partial derivative with respect to x. Now, let's find our partial derivative with respect to y. So I've got 2 terms containing y, the first and the third. So the first term, the derivative of xy with respect to y, is just x. We hold the x constant, treat it like a constant. So if that were 3y, the derivative would be 3. It's xy, so the derivative is x. Now we have the next one, yz squared. The derivative there is just z squared. So this is plus z squared. Both of those terms containing y have y as a linear factor. So y is there with multiplicity 1. It's a linear factor in y. So the derivative is just the constant coefficient. And in this case, those happen to be variables, right? But they're constant relative to y. They're not changing in the y direction. Okay? All right, so now we have our partial derivative with respect to z. So I've got two terms containing z, the second term and the third term. So I've got y times z squared multiplied by the 2. So we get 2yz for the second term in the entire function. So we get 2yz plus, and then x times z, the derivative of xz would just be x because we're differentiating with respect to z. And there we have it, 2yz plus x. So my hope is that this is a very straightforward exercise for you. It can get a little bit confusing if we start to look at all the different variables and the exponents and the trig functions and all of that, but don't let any of that throw you. Treat everything like a constant except the variable that you're differentiating with respect to. All right, so now let's go back and talk about those higher order derivatives. I kind of showed you a little bit about the notation for it, but let's go ahead and dive into those and take a closer look at those. So higher order partials. Okay, so suppose I have got the partial derivative of my function with respect to y. Okay, and maybe I want to take the derivative of that, the partial derivative of that result with respect to x. Then we would write that out front, right? We're always, you don't really need the parentheses on the front one. We're taking the partial derivative of with respect to x of the partial derivative that we already took with respect to y. That's what this is saying. So this is equal to the partial squared of the partial x partial y. And in this form, we are taking those derivatives kind of in reverse order that you see in the bottom, right? We're going to do the partial with respect to y first, then we'll come back and do the partial with respect to x. Okay, now if we were to write that with the subscript notation, that's going to be equal to the partial derivative y x of xy, because we're going to take the derivative with respect to y first, then we're going to take the partial with respect to x next. Okay, so here I really want you to see that in this notation, the order is reversed. So the order is reversed. We do partial y first, then we do partial x. Okay, so that order is reversed. We're working from right to left. Here, however, in this notation, we're working the derivatives from left to right. So we took the partial with respect to y first, then we take the partial with respect to x next. Okay, so this one we're going to read left to right. So the derivatives occur from left to right, partial with y, then partial with x, etc. Here in the partial derivative notation, using the actual partial, that is going to be the reverse order of what we see in the denominator. So that's not confusing at all, right? Right. It's really not as bad as all that. It's really not. So because of the cumbersomeness of the partial derivative notation, a lot of times we prefer to write the partials using the subscripts. However, you will see the partial derivative notation and you will be expected to know what it means and in what order you're supposed to take something. So just to clarify that, let me write this down. If I have got the partial derivative with respect to x of the partial, you know what? I'm not even going to give it to you that way. Let's do this. Let's do this. So suppose I said, hey, I want the partial squared, partial x, partial y of f of x, y. This is telling you we're going to take the partial derivative with respect to y first. Then we'll take the partial with respect to x of that partial. Okay, so that's what that's getting at. So you do need to understand that this is being worked in reverse, just like any other function notation. You work inside out, or from the furthest thing to the right, and then work our way out through the nested functions, or nested operations, I should say. All right, so these are called second partial derivatives because we're taking a second derivative. And because we have choices here, we have two different ways we can go each time. There are a total of 4 second partial derivatives. So there are 4 second partial derivatives. So we have the partial squared of f with respect to x squared, so that is the partial with respect to x twice. There is the partial squared of f with respect to x with respect to y, so partial x, partial y. That's going to be fy, darn it, fy x, because we do take the partial with respect to y first. Then we have the partial squared, that looks like a 2, sorry about that. Try to keep them looking more like backward 6s. The partial squared of f with respect to y x, so that's going to be fxy, because we're taking that partial with respect to x first. Then we have the partial derivative with respect to y twice. So that's fyy. Okay, so let's go ahead and do an example where we see these partial derivatives in action. So let's do this example. Find all second partial derivatives of f of xy equal to x e to the x squared y. Okay, so we just saw this a moment ago, and I chose this intentionally. We already have the first derivatives, so we know the first partials, rather. So we know the partial of f with respect to x is equal to e to the x squared y plus 2x squared y e to the x squared y. And we know the partial derivative with respect to y is equal to x cubed e to the x squared y. Okay, so I'm going to go ahead and mark these with 2 different colors so we can keep track of them. So the partial with respect to x will be green and the partial with respect to y will be yellow. Okay, so we are now going to find those partials. So fxx, so that's the partial with respect to x, and then we take the partial with respect to x again. So we begin with fx, so the green. Okay, so we're beginning with green here. So I'm going to underline that. Then we're going to take the partial of each term here with respect to x. So for the first term, we have e to the x squared y, so that's e to the x squared y, chain on the derivative with respect to x, so that's going to be chaining on 2xy plus. Okay, now we do the next term. Well, here we're going to have to use product rule because we have an x squared being multiplied to e to an x squared. Okay, so notice I'm ignoring y's. I don't really care what y is doing. Y is just constant as far as this operation is concerned. So I'm going to use the product rule here. So I've got 4xy times e to the x squared y. So just so that you can see it, how I'm dividing this up, I'm kind of thinking of it in this way for my product rule with respect to x. All right, plus, now I'm going to leave the first term, 2x squared y, and multiply by the derivative of e to the x squared y. Well, as we've seen before, the partial with respect to x of e to the x squared y is going to be 2x e to the x squared y. I'm sorry, 2xy. Drop my y. 2xy e to the x squared y, because the y is just constant with respect to x. So just like you would multiply by any other constant, it's just going to stay there. Okay, and we can simplify this a little bit. First of all, I noticed that every single term has an e to the x squared y, so it might be easiest if we pull that guy out to the front there. And then that'll leave me 2xy plus 4xy, which is 6xy, plus 2x squared y times 2xy. So that's going to be 2 times 2 is 4, x squared times x is x cubed, y times y is y squared. Okay, so this was just an algebraic step. So you can see we have an x e to the x squared y in every term. I factored that out, combined the like terms here and here, and this was not a like term, that was something different, so we left that added there at the bottom. And there we have it. You can leave the e to the x squared y distributed. That's entirely up to you. That's perfectly fine. Okay, now let's do the partial, the second partial with respect to y twice, so fyy. So now I'm looking at strictly the yellow here because I'm not interested in the green over there. Just f sub y, we've got that. So now we're going to take the partial derivative of that with respect to y again. So once again, x cubed is constant with respect to y, so there's no product rule needed. So we've got x cubed times e to the x squared y, chain on the derivative of x squared y with respect to y, which is x squared. So this is going to be x to the 5th e to the x squared y. Okay, so now let's go ahead and take the mixed partial. So mixed partial just means that we're doing it with one variable and then the other, right? We're mixing it up. So now let's find fxy. So I'm going to begin by looking at fx, and then I'm going to take that partial derivative with respect to y. So let's see what we get. So the partial derivative with respect to y of e to the x squared y is going to be x squared e to the x squared y. Chaining on the derivative of x squared y, which is just x squared, because x is constant relative to y. Okay, so then I want to take the derivative 2x squared y e to the x squared y, and as you can see, the y appears in both parts of, in the product as just y and also as part of the exponent on e. So we've got to treat this again as a product rule. So the first part, 2x squared times y, the derivative with respect to y is 2x squared, times the second part of the function, which is e to the x squared y, or the second part of the term, plus, now I take the first part, 2x squared y, and I multiply by the derivative with respect to y of e to the x squared y. So that's e to the x squared y, chain on, x squared. All right, so I'm going to go ahead and factor out the e to the x squared y again just to make it easier to digest. So that's e to the x squared y times x squared plus 2x squared is 3x squared, plus 2x squared y times x squared would be 2x to the fourth y. Okay. All right. So now let's go ahead and find the next partial derivative. So the next one's going to be fyx. And because y is listed first here in this notation, we are using the f sub y first and then taking the derivative of that with respect to x. Just so that we can see it, since I've rolled it off screen, I'm going to rewrite fy here. So fy was equal to x cubed e to the x squared y, just so that we have reference. All right. So I'm going to take the derivative of that with respect to x, and I am going to need to use the product rule here because I've got an x in the first part multiplied by e to the x squared y. So because x appears as both part of the, the term itself and then as the exponent in e, we have to treat it using product rule. So the derivative of x cubed with respect to x is 3x squared times the other function e to the x squared y, plus, now x cubed will remain constant, will remain untouched, and we have e to the x squared y. So the derivative of e to the x squared y is going to be 2xy, because we're taking that derivative with respect to x. Okay, so let's go ahead and factor it out. We get 3x squared. I wanted to factor out e to the x squared as I've done on the others. E to the x squared y times, all right, 3x squared plus x cubed times 2xy would be 2x to the fourth y. And there we have our second partial derivative, where we have first taken the derivative with respect to y and then with respect to x. So I want to take this opportunity to point something out to you. What do you notice about the first mixed partial that we found and the second mixed partial that we found? They're identical, right? These are identical, and that is always going to be the case with mixed partial derivatives. So we're going to find that this is always the case. The mixed partials are always going to be equal to each other. We're going to find that the partial derivative of f with respect to x and then y is equal to the partial derivative with respect to y and then x. That will always be the case for mixed partial derivatives. All right, so let's do one more example, and this time we're going to take it to slightly higher dimensions again. We've got example f of x, y, z equal to y e to the x plus x ln of z. Okay, let's find the partial derivative f z z x. So what that's asking me to find is the third partial derivative with respect to x z squared. Remember, we work from right to left when it's in this notation. Okay, so we're going to find this partial derivative. So we begin by finding fz. Well, that's nice because the first term doesn't have a z in it. The first term is constant with respect to z, and therefore that's equal to 0. The second term, x ln of z, x is constant with respect to z, so it's just x. The derivative of ln of z is 1 over z. So that's just equal to x over z. Okay. Now let's find fzz. So that's going to be x over z, so x is constant, that will remain, and then this becomes negative 1 over z squared. So we get negative x over z squared. Finally, we find the partial derivative with respect to x of the previous partial that we found. That's just going to be negative 1 over z squared. Okay, it's just like having a constant multiplied by x. And there we have it. Okay. All right. So now let's do this and see if it holds true in this higher dimension that the mixed partials are all equal. So now let's find fzxz. Okay, so just to keep this in sight, I'm going to say let's find fzxz. So we need our partial derivative with respect to z again, which we already know is x over z. Now we take the partial derivative of that with respect to x. So that's just going to be 1 over z. And now the partial derivative of that with respect to z is going to give me negative 1 over z squared. So yep, worked again. All right, so let's do one more mix-up. Let's take it with respect to x first, then find our partials with respect to z. Okay, so fxzz. Okay, so I need fx first. We have not found this yet, so let's do that now. Y e to the x, y is constant, so it'll just be part of the product. E to the x derivative is e to the x, plus the derivative of x ln z with respect to x is just ln of z. Now we find that partial with respect to z, not y, z. So the first term has no z in it, it goes to 0. The second term is 1 over z, and then when we take our partial derivative of that with respect to z, we get 1 over z squared. Okay. So you can see that these partials are going to hold up all the way through. And we have a good example right here. fzx and fxz are the same, even though this has 3 variables in it. The partials are the same if it contains the same number of derivatives of the same type. So like a zx and a zy obviously wouldn't be the same, but zx, xz are going to be the same because it has the same number of partials relative to the same variables. And I do believe that is all I have for this section. As always, if you have any questions, please let me know.